So we've seen in various problems that defining the first time that something happens as a random variable can be very useful. So in here we're in the context of the Brownian motion, and some possible questions are along the lines of kind of going back to this Brownian particle example. So what is the first exit time of the Brownian particle from the confines of that box? What's the first time that blue dot reaches one of the edges, one of the 6 edges in that three-dimensional box. And here we're going to do this in one dimension by setting a positive level b. So this is a positive number, and TB will be defined as the very first time that the standard Brownian motion hits the level b. This would be the mathematical way of writing it. The very first time is the minimum over the set, at which b at time t actually realizes that level. So here are a couple of examples where obviously the sample paths of the Brownian motion are random. So here's one example of one path where we move down and then kind of quickly move up, reaching the level b. If you ever cross the level b, because the Brownian motion is continuous, that time exists somewhere in between these two times when it was below b and above b. So somewhere there was a crossing point, and that point is what's going to define this particular outcome of the random time TB. Here is another example where the Brownian motion goes up but doesn't quite reach the level b, goes below and kind of meanders below 0, and then finally goes moves all the way up, and here there's a crossing point where it finally crosses the level b, and that defines this outcome of the random time here, and so on and so forth. And so TB is going to be a continuous random variable, so it takes values in the non-negative continuous random non-negative real numbers. And one could even try to think about whether that random variable, that random time, can be infinite. We've seen in the context of Markov chains that some of these random times can be can take on the value infinity with a positive probability. That was related to the concept of recurrence, and here same thing could potentially happen. We'll see whether that's actually true. We'll see if TB could potentially be infinite with positive probability or not. But for now, if you have a continuous random variable on your hands, you kind of want to, in order to be able to run various calculations, various expectations, compute various probabilities, you'd like to know its one, cumulative distribution function, and maybe two, the density, which is the derivative of the cumulative distribution function. So what lets us do this, this is one of those rare examples where you can actually have a computation in an explicit form, and the theorem that gives us this, we'll prove this during the lecture, is this reflection principle, which says that the probability that TB is below time t, so you set some little time t, perhaps it's here, and you're looking at what is the probability that this random variable occurred before, meaning the Brownian motion went up and crossed the level b prior to this deterministic time. So that's the probability we're interested in, and we'll if we can compute that out, we'll also then take a derivative with respect to t, and then have the density that would that we can integrate against. So the reflection principle is going to tell us that probability, that CDF, is equal to 2 times the chance that the Brownian motion at time t exceeds the level b. We'll see how the name reflection comes about. That it's related to that factor of 2. There's going to be this we're going to exploit the symmetry of the Brownian motion up and below the level b, and hence kind of reflect and pick up that factor 2. So we'll see how that happens. But for now, we kind of want to just give this a little bit more explicit form. Instead of just writing it as this expression, we want to bring it to some kind of bring this CDF into some nice clean form, and then take the derivative, and this is what I'm doing here. So what's the probability that BT exceeds the level B at time t? Well, BT is normally distributed with mean 0 and variance t, and so you need the probability density of a normal random variable with variance t. That's what's inside this integrand, and then obviously I'm going to be integrating from b out to infinity. So this is, I guess, a related picture in terms of a slightly different density, which I'll discuss, but the concept is the same. We're integrating the probability mass function out, past the level b. So if this plot was for the integrand here, I would not have the square root of t factor here, and I would just integrate from b on outward and compute the area under that curve, which would give me that what's called exceedance probability, the probability that BT exceeds little b. The next thing we kind of notice is that there's sort of two variables here. There's the variable b, little b, and then there's a variable t. And we kind of want to think of one as fixed and one as moving about. The CDF, this CDF here, is a function of t, and we're going to, for that reason, treat b, little b, as fixed. So we're fixing the level b, and in order to measure this cumulative distribution function, that probability, we're going to think of t as a variable. And so here this variable is kind of buried inside this exponent there. And so we need to try to kind of extract it somehow, and kind of various tricks you can play here with, say changing variables. If I'm trying to get rid of the t there, why not set x equals y the square root of t, which is going to cancel out my t there upon squaring. That's exactly what happens here. So I'm able to remove the t from the exponent. I'm doing all this to be able to kind of write everything clearly as a function of t, so that I can later take a derivative. And once that's done, I guess there's one more part where dx, you can from here compute the dx dy, which gives you formally this equivalence between dx dy and the square root of t here, and so that's one of the reasons, I guess that is the reason why that the square root of t disappears in the square root in the denominator there. So that the square root of t here is responsible for canceling that one there. And the final thing is fixing the limits. So as x runs from b to infinity, y clearly then runs from b over the square root of t up to infinity. So that gives me the limits for this integral. I then can write it in terms of the normal density. So this integral represents, again, kind of revisiting this calculation here, this integral is computing the area under the curve past the point b over the square root of t. And notice that we've managed to get the t all the way out to the limit and removed it entirely from what's inside. This is the standard normal density, and then we're later in a second going to have phi, which is the standard or the cumulative distribution function of the standard normal. So we've seen these integral tables where you have both of them in a number of integrals that you can kind of use. So this is one example of making something that's slightly non-standard look standard, so that you can then look up some integral and have an explicit expression that you can use. So next, what's the next thing? Like we've already mentioned in the previous lecture, it's we kind of often try to write things down in terms of the cumulative distribution of the standard normal random variable. So that's what I'm working on next. So this is computing, the limit here is a little bit an awkward form. It's computing from the lower to the upper. I know that the entire integral here will add up to 1, so the integral of phi of x, the standard normal, has to compute out to 1 because it's a probability density function. And so the area that I've left out that I didn't integrate, 1 minus that is just the shaded area here, and that's exactly what happens. So here I'm subtracting from 1 the complement of this integration, meaning I've compute the integral, from below the level b over the square root of t in here, and subtract it from 1 to recover the area under the curve, which is what we originally had. And then here you kind of finally have a clean expression in terms of this standard normal cumulative distribution function. So these are the definitions, and like I already showed, that this is what they are. So big phi, that prime there means derivative, is equal to little phi, the density, and then similarly, it's just this. So finally, to conclude, we just want to get the density out now. How do you get the density? You take a derivative. So we're taking a derivative of, I guess, 2 times this. So remember, we just computed that exceedance probability. We need to times it by 2 and take a derivative with respect to t. So let's quickly do that. I pick up the 2 from that multiplication. The 1 minus doesn't do anything. When I take a derivative of a constant, I get 0. So I pick up a minus sign. So that explains the minus 2 in the front coefficient there. And then my remaining term is just a derivative of t phi of this argument, which isolated the t pretty cleanly. So this was the whole kind of point of us doing this change of variables, is that we were able to remove the phi from inside the integral and bring it into this argument. And now there's a kind of just a clean way of, how do you take a derivative with respect to t of something like this? It's the chain rule, derivative of the function and then the derivative of the argument. So the argument is just b t raised to the minus 1/2. The derivative of this is this quantity right there. That cancels out the 2. It also cancels out the minus sign. That would have been a concern if we got a negative density. We want to make sure that we're getting something positive, because probability densities have to be positive. And that leaves us with this number in the end, this value, and which expands out to this quantity here. So again, there are 2 variables, b and t, but in this setting we're really thinking of t as the free variable. It's the variable that's defining this CDF as a function. And so b is something that you think of as fixed, and this density has a number of different kind of dependencies on t. One is in this exponent, and one is in the denominator here. So you can see with increasing t, this will make the density decay. So this term is responsible for the decay of the density out to infinity. So the probability that this time becomes larger and larger gets smaller and smaller because of this term here. This does the sort of exact opposite. When t becomes large, this term becomes sort of larger and larger until it gets up to 1. Right? This is at most 1. So this term is bounded above by 1. And as we take t larger and larger, this grows slightly up to 1, and this inverse proportion here is making the density decay. So you see the usual decay of the probability density function out to infinity, as it should, because presumably this better integrate out to 1. So we can try to verify that to make sure this is really a valid expression of a probability density function. And then if you want to look at the probability density function around 0, so this, by the way, this density is defined on the half real line. T must be greater than or equal to 0, and you can try to think about what this expression would be if we were to isolate some small neighborhood around 0. We're kind of asking, what is the probability mass, or the chance or likelihood of these random times being concentrated close to the origin. And you can sort of see when this is small, this gives us a decay. So a small number here would give a large exponent, which brings us down, and this one does the exact opposite, where if this is small, this quotient here, it actually becomes very large. And so you have sort of 2 terms that are kind of driving the density in 2 different ways. One is I guess, increasing in t, and the other one is decreasing in t. And then when you take d down to 0, the opposite, this one is increasing as t becomes small, and this one is decreasing as t becomes small. So we'll look at the implications of all this, I guess, next, and look at a few calculations, and then we'll prove that theorem there.